July 21st, 2023. A routine set of commands goes out from a control room in California to a spacecraft that has been flying for 46 years. Nothing about the moment feels historic. It is just another line item on a long checklist. Another Tuesday in a mission that has already survived Jupiter, survived Saturn, survived Uranus, survived Neptune, and survived nearly 5 decades. In the coldest, emptiest, most unforgiving environment human engineering has ever attempted to operate inside. And then, without warning, without an alarm, without anyone in that room immediately realizing what had just happened, the spacecraft goes silent. Not weak, not glitchy, silent. 12.3 billion miles away, a machine that has been talking to Earth since before most of the people currently working on its mission were even born simply stops answering. And for the next 2 weeks, nobody, not the engineers who built backup systems for exactly this kind of failure, not the scientists who have spent entire careers reading its data, not anyone, inside NASA's Jet Propulsion Laboratory, knew for certain if it would ever speak again. This is the story of Voyager 2, the quieter, less famous twin of the spacecraft that gets most of the headlines, the one that actually pulled off something no other machine humans have ever built has managed to do, before or since. And this is the story of the 2 weeks in the summer of 2023 when it went dark, the desperate plan NASA used to try to wake it back up, and what scientists found buried in its data once it finally answered. Information that quietly rewrote what we thought we understood about the edge of our own solar system. Let's go back to where this machine actually came from, because most people do not realize how strange its history already was before 2023 ever happened. Voyager 2 launched from Cape Canaveral on August 20th, 1977, 16 days before its twin, Voyager 1, even though it carries the number 2. Its original assignment was simple on paper: fly past Jupiter, fly past Saturn, take pictures, send data. Then go quiet somewhere in the outer dark. Its job finished. Nobody expected what actually happened next, because of an extraordinarily rare planetary alignment that occurs roughly once every 175 years. An alignment where Jupiter, Saturn, Uranus, and Neptune all sit on the same side of the Sun at once. Engineers realized Voyager 2 could use the gravity of each planet to slingshot itself to the next one. It became the only spacecraft in human history to complete what NASA still calls the Grand Tour. Jupiter in 1979, Saturn in 1981. Uranus in 1986, the only spacecraft that has ever visited that planet still to this day. And Neptune in 1989, the only spacecraft that has ever visited that planet either. At Neptune, moving faster than 34,000 miles an hour, Voyager 2 skimmed just under 3,000 miles above the cloud tops, discovered new rings, discovered 6 new moons, and captured images of the Great Dark Spot, an enormous storm system larger than the Earth that had never been seen before and that had actually vanished by the time Hubble looked for it years later. Then it kept going. On November 5th, 2018, Voyager 2 crossed the heliopause, the outer edge of the Sun's protective bubble, and became only the second human-made object in history to enter interstellar space, following its twin, Voyager 1, which had made that same crossing back in 2012. 2 machines, launched the same year, built in the same facility, now the only 2 objects our species has ever placed outside the boundary of our own solar system. And by the time the summer of 2023 arrived, Voyager 2 was still working, still transmitting. Still, somehow, after 46 years in the vacuum, sending back real scientific data from a region of space no human instrument had ever occupied before. Which is exactly why what happened on July 21st mattered so much. Here's what actually went wrong, and it is almost unbearably small when you consider the scale of the consequences. As part of a routine sequence of commands sent to the spacecraft, a coding error caused Voyager 2's high-gain antenna, the 3.7-meter dish that is its only connection to Earth, to tilt 2 degrees away from where it needed to be pointing. 2 degrees? That is it. 2 degrees out of a full 360. At the distance Voyager 2 was sitting more than 12. 3 billion miles from Earth, a shift that small was enough to take the spacecraft's entire signal and send it past our planet entirely, missing us completely, radiating instead into the emptiness beyond. Voyager 2 was still alive. Its systems were still running. Its instruments were most likely still collecting data exactly as they were supposed to, but it could no longer hear us, and we could no longer hear it. For a machine that depends entirely on radio contact for every command, every update, every piece of information it has ever given us, that 2-degree error was the equivalent of a phone call being placed into a void with nobody on the other end and no way to know if anyone would ever pick up again. Under normal circumstances, this kind of problem would not have been catastrophic. Voyager 2 has an onboard safety routine, a fail-safe built in decades ago that automatically reorients the spacecraft's antenna back toward Earth several times a year in case exactly this kind of drift ever happened. But that automatic reset was not scheduled to run again until October 15th. That meant, in the worst case, that NASA was facing almost 3 full months of complete silence from a 50-year-old machine in interstellar space, with absolutely no way to reach it, and no way to know, until the reset actually happened, whether the spacecraft would even survive that long undisturbed, drifting through a region of the cosmos more hostile and less understood than almost anywhere else humans have ever tried to operate a piece of hardware. The team at JPL did not wait to find out. Within days, engineers turned to the Deep Space Network, the array of massive radio dishes NASA operates around the globe, specifically to keep in contact with spacecraft like this one. Using multiple antennas at once, straining to detect anything at all coming from that direction in the sky, the team managed something that felt, by their own admission, like an enormous stroke of luck. They picked up a carrier signal. Not data, not telemetry, just the faintest possible heartbeat, a bare radio tone confirming that Voyager 2's transmitter was still alive and still broadcasting, even if the message itself was going nowhere near Earth. It told them the spacecraft had not died. It told them there was still conceivably something to save. But a heartbeat is not a fix. Voyager 2 still could not hear anything sent to it because its receiving antenna was still pointed 2 degrees away from home. And this is where the story turns into one of the most audacious things NASA has ever attempted with a piece of 46-year-old hardware. On August 2, 2023, engineers at the Deep Space Network's Canberra, Australia facility prepared something they internally called an interstellar shout. Under normal operation, the Deep Space Network sends its commands at standard power, more than enough to reach a spacecraft whose antenna is properly aligned. But Voyager 2's antenna was not aligned, and normal power was not going to cut it. So the team dramatically boosted the strength of the signal, pushing it up to roughly 100 kilowatts, and aimed it directly at the last known position of a spacecraft they could not currently talk to, sitting more than 3 billion miles away, carrying a single instruction: reorient your antenna back toward Earth. Then they waited. And this is the part of the story that is almost impossible to fully appreciate unless you sit with the numbers. At that distance, a radio signal traveling at the literal speed of light, the fastest anything in the entire universe can travel, needs 18 and a half hours just to complete the one-way trip. 18 and a half hours for the shout to even arrive. And then, if it worked, another 18 and a half hours for any response, any sign that the command had been received and followed to travel back. 37 hours total. More than a day and a half of waiting, with absolutely nothing to do but wait, after firing off the most powerful signal NASA had ever aimed at this particular spacecraft, not knowing whether a 50-year-old antenna sitting in the freezing dark of interstellar space would receive it, understand it, and physically move in response. The team itself described the odds going in as low, not because the command was wrong, but because there was no guarantee the shout would be strong enough, precise enough, or that the spacecraft systems, after nearly 5 decades of continuous operation, would respond the way fresh hardware would have on a test bench back on Earth. There was no backup plan for this specific attempt. If it failed, the only remaining option was to wait out the months until Voyager 2's own automatic safety reset kicked in on October 15th, and hope the spacecraft was still healthy enough by then to still matter. The command had gone out. It was either traveling correctly through the dark toward a target more than 12 billion miles away, or it was not, and there was no way to know which until the full waiting period had run its course. Engineers who had spent entire careers on this mission, some of whom had joined Voyager before several of the spacecraft's own instruments were even switched on, could do nothing but sit with the uncertainty. Every hour that passed without a signal was not necessarily bad news. The mathematics of the delay meant it would take exactly that long either way. But every hour still felt heavier than the last, because somewhere out past the edge of everything, humans have ever physically touched. A 50-year-old machine was either turning itself back toward home or it was not, and the answer had already been decided. In the first fraction of a second, the shout reached it. Everyone on the ground was simply waiting to find out what had already happened. At 12:29 in the morning, Eastern Time, on August 4th, 2023, data began streaming in again. Real data, full telemetry. Voyager 2 was not just alive, it was operating normally, still on its expected trajectory, still doing exactly the job it had been doing for 46 years. The interstellar shout had worked. A signal sent across more than 12 billion miles of space had reached a spacecraft older than most of the engineers who sent it. And that spacecraft had listened and obeyed and turned itself back toward the only home it has ever had. Now here's the part almost nobody outside the mission ever heard about, the part that turns this from simply a great recovery story into something scientifically significant. Because when Voyager 2 came back online and researchers went back through what its instruments had been recording, both before the blackout and in the years surrounding its 2018 crossing into interstellar space, they confirmed something genuinely strange about how this spacecraft's journey compared to its twins. When Voyager 1 crossed the heliopause back in 2012, the transition was messy. It took about 28 days of back and forth, with the spacecraft detecting brief episodes where it seemed to be connected to both the solar wind inside the bubble and the interstellar medium outside it, before the crossing was considered complete. Voyager 2's exit, 6 years later, was almost the opposite. It happened in under a single day. A clean, sharp departure from the heliosphere into the space between the stars. And the reason scientists could even see that difference so precisely comes down to one critical piece of hardware. Voyager 2 still had a fully working plasma science experiment, an instrument capable of directly measuring the density, temperature, and flow of the plasma around it. Voyager 1's equivalent instrument had failed decades earlier, forcing scientists to infer plasma conditions around it indirectly through other measurements. Voyager 2 could measure it directly. For the first time in human history, we had a hard, direct read of what plasma actually looks like on both sides of the boundary of our own solar system. Not an estimate, an actual measurement. And what that measurement revealed did not fully match what scientists expected. Researchers publishing across 5 separate papers in the journal Nature Astronomy in November 2019 described something unexpected in Voyager 2's data. Even after its clean exit from the heliosphere, the spacecraft was still, detecting particles that appeared to be leaking outward from inside the bubble, mixing into the interstellar medium beyond where the boundary was supposed to be sharp and absolute. The edge of our solar system, it turned out, was not the crisp, clean line the models had assumed. It was porous. Then, in October 2020, a further analysis of the plasma density data coming from both Voyager spacecraft together revealed something that genuinely surprised the researchers studying it. A significant and unexpected increase in the density of the plasma the farther the spacecraft traveled beyond the heliopause. This was not supposed to happen the way it was happening. Scientists described it as evidence of a large-scale density gradient in the very local interstellar medium. In the general direction, our solar system is currently moving through the galaxy, a structural feature of the space immediately outside our solar system that no model built before Voyager actually got there had predicted. It gets stranger, because Voyager 1 exited the heliosphere from what scientists call its northern hemisphere, and Voyager 2 exited from the southern hemisphere, at a completely different location along that boundary. And the fact that the two crossings looked so different from each other, one messy and gradual, one clean and sudden, tells researchers that the heliosphere itself, the giant magnetic bubble that has protected every living thing on Earth for the entire history of life on this planet, is not a simple, symmetrical sphere the way it is so often illustrated in diagrams. It might be closer to a comet shape, with a long trailing tail stretching out behind the solar system as it moves through the galaxy. Or, and this is a real possibility researchers have raised, it could be shaped something closer to a croissant, asymmetrical and irregular in ways nobody has directly observed yet, because neither Voyager spacecraft has ever traveled through the wake side of that bubble. We simply have no data from that direction, and no spacecraft currently on a trajectory to ever collect it. Which brings the story back to 2023, and to right now, in 2026, because the recovery of Voyager 2 after its 2 weeks of silence was not just a rescue of an aging machine. It was a rescue of the only functioning instrument humanity has ever had that could keep collecting this specific kind of data, direct plasma measurements from inside the very local interstellar medium, at the exact moment the sun was heading toward a period of increased activity, a solar maximum expected around 2025, when eruptions on the sun's surface send shockwaves outward that Voyager's instruments can detect passing through the interstellar plasma around it, effectively letting scientists watch ripples move through a part of the galaxy no telescope on Earth has ever been able to observe directly. But the clock on all of this is now running out, and it is running out fast. The radioisotope thermoelectric generators that power both Voyager spacecraft, essentially containers of decaying plutonium converting heat into electricity, are not being replaced and never will be. Each spacecraft loses about 4 watts of power every single year, permanently, with no way to reverse it. In April 2023, just months before the antenna crisis, engineers at JPL had already started dipping into a reserve of backup power that had originally been set aside for one of Voyager 2's onboard safety systems, just to keep its 5 scientific instruments running a little longer. Then, in October 2024, NASA made the difficult call to permanently switch off Voyager 2's plasma science instrument, the very instrument that had given us that unprecedented direct read of the heliopause crossing back in 2018, in order to preserve enough power to keep its remaining instruments alive. Its cosmic ray subsystem is scheduled to be shut down sometime in 2026. One by one, the tools that let this spacecraft see are being permanently switched off, not because they are broken, but because there simply is not enough electricity left on a 49-year-old machine to run them all. As of February 2026, Voyager 2 sits approximately 143 astronomical units from Earth, roughly 21. 4 billion kilometers, or about 13. 3 billion miles away, drifting through the constellation Pavo at more than 34,000 miles an hour, a distance so vast that a radio signal now takes close to 20 hours just to travel one way between the spacecraft and mission control. Engineers currently believe both Voyager spacecraft could continue operating at least one science instrument into the early 2030s, if nothing else goes wrong. But they have also been careful to say publicly that after 49 years in the harshest environment any human-built object has ever endured, unexpected failures could shorten that timeline at any moment. There's no repair mission possible. There is no way to send more power. There's no way to send a technician. Every single decision the Voyager team makes now is final. The moment an instrument is switched off, it is very likely never coming back on again. And there is no replacement waiting in line behind it. No other spacecraft currently exists that is capable of reaching interstellar space and collecting this kind of data within the next several decades. If Voyager 2 goes silent permanently, whether from a power failure, a random hardware fault, or simply outliving the last watt its aging generators can produce, the specific window it opened into the plasma physics of the space immediately surrounding our solar system closes with it, and stays closed for a generation, maybe longer, which is what makes those 2 weeks in the summer of 2023 matter so much more than they seemed to at the time. A tiny coding error, a 2-degree tilt of an antenna older than most of the people reading about it, nearly ended the only continuous direct measurement humanity has ever had of the boundary between our solar system and the rest of the galaxy. And it was saved, not by a repair mission, not by new technology, but by a single desperate boosted radio shout fired across more than 12 billion miles of empty space, on the hope that a machine built in 1977 would still be listening on the other end. It was. And because it was, we know things about the edge of our own solar system that we did not know before, that the boundary is not clean, that the density beyond it is not what the models predicted, that the shape of the very bubble protecting every living thing on this planet is stranger and less understood than we ever assumed. Think about what almost slipped away in those 2 weeks. Not just a piece of hardware, but the only direct window our species has ever had into the plasma physics of the space immediately surrounding our own solar system, the region that has quietly shielded every living thing that has ever existed on this planet from the harsher radiation of the wider galaxy. A 2-degree error very nearly closed that window for good, months before anyone would have even known it was permanently shut. Voyager 2 is still out there right now, still moving, still sending back its thin signal across the dark, carrying on its side a golden record with the sounds of Earth, greetings in 55 languages, and 90 minutes of music from across human history, a message meant to outlive every single one of us. One day, nobody can tell you exactly when, the last watt of power will run out, and the last signal will make its long journey home, and after that, there will be nothing but silence and a machine. Drifting forever through the dark, it helped us finally begin to understand. Until then, it is still listening and it is still talking, and for as long as that lasts, we need to keep paying attention. If this is the kind of story you want more of, subscribe and let me know in the comments. What part of this surprised you most?